within minutes. So what are we measuring now? We're measuring some relationships based upon the present half-lives that have no bearing upon the initial conditions. That's what we're saying. The initial conditions were totally different from what they are now. So the half-lives were totally different. The rates of decay were totally different. They were extremely fast. Okay? That's the bottom line to this. I mean, these are the results. I eliminated all the complications as much as possible of all the details of the calculation. I'm going to revise this paper in more critical revision of it. And those of you who are really into this stuff would like a copy of that, I'm perfectly willing to give you a copy, eventually being able to publish it sooner or later once I get over all the hurdles. It's really hurdles when you deal with this because you can't buck City Hall, you know. If you try to publish it in the open literature, forget it. If they don't kill you on the day, they'll kill you in some other way. So it's hard to do. So we're going to probably have to just publish it in creation circles, and that's good enough to get the word out, right? All right, I want to deal with one more thing here. This is a question. I'm not going over it again, but you can relate this in this kind of equation. That's an equation that's simply a straight line. So if you measure the decay energy, or determine it in any kind of way, and look at the decay rate process there, okay, then that's simply an equation of a straight line. And you can fit that to a straight line, and you can fit all of those data to a straight line, actually. In fact, here's the uranium, all the isotopes, the thorium, samarium, rubidium, potassium, all of them. There's data in here which you don't need to know about. It's spin sensitive, but you don't need to know that. These are the equations that govern that. And this is a confidence coefficient to fit those equations with that degree of reliability. So you got pretty good confidence coefficients here, better than 90% for sure. And that means we got pretty good fits for these data as statistics go, right? So a linear relationship correlating the energy with the decay rate is a very valid way of looking at this. Conclusion, accelerated radioactive decay rates are the consequences of the magnetic energy perturbations that occurred when? In the primordial plasma state. Rapid dissipation of energy. Where did all the energy go? Results as the radius of curvature expands, inducing temperature decreases. Now that's a thing that Humphrey's related to. Now that's all related back to the expansion of the universe. We're just particularizing it to the expansion of the Earth, okay? Now I don't necessarily have to use this. There are other ways of doing this. I can use Laplace's cooling equations and get results, and I have done that, but this is one result that was already on the slide. There's a temperature at the initial time when it was a plasma. Here's the temperature, average temperature at the surface, about 300 degrees. Initial radius of curvature would have been about this much. Final radius of curvature would have been about this much. And the point is, it's an equation that is related, according to Humphreys, by this, that the temperature is inversely related to the square of the radius of curvature, okay? Now, if we took that, which is called the proper time t, use this information with another equation, and that's a complicated equation, and it's Humphrey's derivation. The time is related to these radii of curvature, and you can see that when I use that, I get a number. Or did I miss it? Where am I? Yeah, here's a number. 14.7 hours time to cool off. From how much? 10 billion degrees to 300 degrees. 14.7 hours. Well, listen, 2.5 days of creation, another half a day to cooling off, and the plant life in Scripture says what? Third day? No problem. Everything's cool, right? In the vernacular. Okay, I'm introducing this because Brian asked me to do so. I did some work with the Lucas-Bergman model. The Lucas-Bergman model is envisioning the particles, the electrons, and the protons as rings. Call them a torus. Here they are. This is the torus of the electron and the proton. You can step it up into a helicon. The helicon simply has domains within the torus, which allows different energy states of the torus rather than just one ring. Now, the idea here is that the electrons and the protons are not point particles, as we learned in basic physics and basic chemistry, but they are actually particles that have dimension, okay? And that's the idea, that they are particles with dimension. Each torus has its own size for a proton and its own size for an electron. The proton is a much smaller torus than the electron. So, the electron's negative, the proton's positive. What happens if the proton sits itself inside the electron? Neutral. What do you have? A neutron, right. So you have a neutron. Now, if I go to, say, potassium-40, which is what I'm dealing with here, and I look at the different shells for these neutrons and protons, and there are ways of doing that, okay? It's called nuclear shell structure.